Hi, this is Mark Weitzman. Welcome back to my channel, Theoretical Physics with Mark Weitzman on YouTube. Today we'll continue with Lesson 8 in the Quantum Field Theory, a Student's Perspective course, version 2. And so today's lesson is Lesson 8, the Path Integral for Free Field Theory, Part 1. We're going to continue with what we did for the harmonic oscillator, and for the most part I'm just going to follow almost exactly what Swinnecki does in his book, Chapter 8. It's a very short chapter, it's 2 pages long, but the problems in the chapter are important, and I'll provide a few more details, and I'll do a couple of problems along the way. So this is part 1, and we use the following, using the following dictionary. Now, dictionaries in physics usually means that we sort of translate from one situation to another, let's say from quantum mechanics to quantum field theory. Sometimes when you have like the ADS, CFT conjecture, you go from, let's say, quantum field theory in the bulk to string theory on the boundary, or vice versa. So it's just a sort of just an easy way to translate what you've already established or what you're conjecturing. So we have our usual coordinates in classical physics, and now in field theory we're going to have a coordinate at every point in space. So that's what the vector x is. This is a classical field. And if we're dealing with operators, like in quantum mechanics, now we use the same notation. Now, if we were in like beginning quantum mechanics classes, we would put the hat there, but we don't really bother with this in quantum field theory. I don't know why that. Well, it won't erase. So you're gonna have to determine what it is by context. So this would be an operator quantum field. Then we have what we call a source term, which usually depends on the time, but now it will depend on space and time. So this is a classical source. And finally, we usually make the translation m squared goes to m squared minus I epsilon. This you can think of as a conversion factor. Or it implements, as was shown in the previous chapters, it implements like a translation where the Hamiltonian goes to the Hamiltonian 1 minus I epsilon. So this is like a trick, and it will just, I don't understand why it does that. And this is just a trick that we use to get convergence in to have some meaning in quantum field theory. So we won't really justify it that much. Now the free field Hamiltonian theory, the free field theory has the Hamiltonian density which we've seen earlier. Now this is just like the harmonic oscillator, except for the gradient term. You could think of it, the gradient term, as like couplings between free oscillators in space, but it just comes from relativity basically. We have to have, you know, in order for it to be relativistically invariant, we have to have a time derivative squared minus a space derivative squared. Um, we'll also write frequently just m squared instead of m squared minus I epsilon till we need it. When we need it, it will be there. So the path integral which is also referred to as the functional integral, for free field theory is, we call it Z0J, and it's defined to be the vacuum to vacuum transition amplitude in the presence of a source. And as we've learned in the previous chapters, it's the integral of d phi e to the I, the integral over all space-time of the Lagrangian, the free Lagrangian, plus J phi. The J phi will enable us to term as a source term, and that will enable us to get some information. So L0 is the Lagrangian density. And it's given by, for a free scalar field, and remember that the metric that Zernike uses is a diagonal minus 1 for time, 1, 1, 1 for the space. So the other symbol there, the d phi, is the funny measure. Somehow it's proportional to the product over all space of like little d, d phi x. Now, this is like a funny measure. Doesn't always converge. Sometimes it changes in a funny way, and we'll see illustrations of this when we get to fermions later in the course. Also, the key thing to understand is that the path integral is now a path in the space of field configurations. So what we think of as happening is, you could think of as a given space-like slice. Let's say at time t equals 0, we have a certain field configuration over all space. We could also put boundaries on space and just have regions that we integrate the path integral. But let's say we're all over all space, and what we do is, we go from one field configuration at the beginning of time, And then at the end of time, then when we have the space-like final time, we have another field configuration. And remember, a field configuration is the value of the field at every point in space. So we can go from, let's say, one field configuration where the field is, let's say, relatively constant, and then maybe it starts varying a lot at another time, and so on and so forth. And we end up going to the final configuration. And we look at all possible paths in this very, very large configuration space. And so that's what we're integrating over. That's what the path integral is. Now we proceed the same way as in the harmonic oscillator. So here we first we define Fourier transform variables in momentum space. V tilde k is equal to the integral of d4k. This is how Czernicki defines it. V of x, and the inverse transformation V of x is equal to, let me get rid of these dots, I don't know why they're there. V of x is equal to the integral of d4k 2 pi to the fourth e to the I k dot x v tilde k. Now, you always, in 4 dimensions, you're going to get 4 factors of 2 pi. Some authors put them symmetrically, like they'll have 2 pi squared here and then a 2 pi squared there. Some put them with one or the other. Czernicki puts them always with the k integral. So this denominator as a 2 pi to the fourth. Also, the signs on the e to the minus ikx and e to the ikx, I think they're pretty standard, that when you go from coordinate to momentum, you have a minus sign and you have a plus sign on the reverse. Okay, also k dot x is the special relativity dot product of the two 4 vectors. Czernicki also writes it just as kx, and this is equal to minus k0t plus k dot x. Okay. And the action, the free action, is given by the integral of d4x, Lagrangian density, plus the source term times the field. So these are both functions of x. I probably should write it as j of x, v of x. Okay. Now, I'll work out one term, which is one more term than Czernicki works out. I'm going to work out the minus 1/2 partial u phi partial mu phi. I'll work out this term, which is the more difficult term anyway. And so let's work it out. We have the integral of d4x minus 1/2 the integral of d4k over 2 pi to the fourth. When we take the derivative down, you have to be careful, but it's going to be like 1 up and 1 down when you take the derivatives. So we'll get an I k mu e to the I kx v tilde k And then we'll have an integral. I made a mistake here. The integral d4k prime 2 pi to the fourth I k mu prime phi tilde k prime e to the I k prime x. Okay, so this is equal to minus 1/2. Now let's just rearrange the integrals. d4k 2 pi to the fourth d4k prime 2 pi to the fourth. The I here, the i's in the two terms give us a minus sign. Then I have a k mu, k prime mu, phi tilde k, phi tilde k prime, integral d4x e to the I k plus k prime. I haven't been distinguishing the vectors. Usually these are 4 vectors, but when I need 3 vectors, I'll put them as 3 vectors. But right now they're 4 vectors times x. So this will just give us a Dirac delta function here. And I have minus 1/2 dot 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 2 pi to the fourth del 4k plus k prime. And now we do the k prime integral is very easy because we have a delta function. So we end up getting minus 1/2 the integral of d4k 2 pi to the fourth. Notice this 2 pi to the fourth conveniently cancels one of the 2 pi to the fourths from the delta function. I have my minus 1. And now I'm going to have k mu, k prime mu. This will lead to k prime equal minus k. So the product of these is going to just be minus k squared. So I'm going to get minus k squared. Get phi tilde k, phi tilde minus k. Okay. And so just canceling out all the signs, we have 3 minus signs, right? 2 minus signs. Oh, I'm wrong here. I had 1 minus sign, 2 minus sign, 3 minus signs. I seem to get something in my mind tells me I'm supposed to get. Yeah, I'm supposed to get 3 minus signs. So I have minus 1/2 the integral of d4k 2 pi to the fourth k squared phi tilde k phi tilde minus k. Okay, so that gives us the answer for that one term. And of course k squared is equal to the vector k squared minus k0 squared. Okay, so It never did this to me before. I hate this software because every time I use it, it works differently and the settings change and it does something to me that bothers me. Okay, so the total S0, the total free action is equal to 1/2 the integral d4k 2 pi to the 4th minus phi tilde k squared plus m squared phi tilde minus k plus j tilde k phi tilde minus k plus j tilde minus k phi tilde k. Now, if you look at these last two terms, you might say, how did we get two terms and why do they have different signs and everything? If you work through it, you'll get one term, but then all we're doing is just taking this they're equal basically. Because we're integrating, we're just taking the symmetric form. So just makes things a little easier down the road. Okay, so now we change variables and complete the square. It's kind of amazing how, like, when you take an algebra when you're a toddler, you don't really think you'll ever use this completing the square stuff, but actually you use it in physics quite often. So let's define a new variable, chi. I'm going to write it like x, but it's really a chi tilde k. Well, actually, it should be a chi, I guess. I don't know why I'm calling it chi. Let me just check something in the book. Yeah, it's a chi squared. G, chi squared, whatever. So chi tilde k is equal to phi tilde k minus j tilde k over k squared plus m squared. Now, Shineki says this is a constant shift, and you might be bothered. This shift seems to depend on k and be different. But really, for each k, you have a separate integration variable. Let's call it, originally it was like phi x, and then it became phi k, or phi tilde k. But these are for each x and k, they are, independent integration variables. So we are shifting each phi tilde k by a constant amount, which is this. All of a sudden it does this. So the measure, since we're shifting by a constant amount, the measure doesn't change, or at least we assert. This is another thing we're sort of asserting. We're asserting that big phi is big chi. And, like I said, there's a lot of things that are like not rigorous, or mathematicians can make more rigorous. We're not going to worry about them. But, so doing that, now we get S0, just making the substitutions, is 1/2 the integral d4k 2 pi to the fourth. We have a minus chi tilde k plus j tilde k over k squared plus m squared, k squared plus m squared. The reason why I'm writing this out is if you try and do it in your head looking at Jarecki, his equation, you'll eventually get it, but you'll make a few, at least I did, will make a few mistakes along the way. So it really sort of does help to just write it out. Then your mind will be able to process it much easier. And you have plus j tilde k everything just doesn't work the way it's supposed to. So if you do that and you carefully multiply everything out, you get exactly what's in the textbook, obviously. So now we get S0 is equal to 1/2 the integral d4k 2 pi to the fourth j tilde k j tilde minus k divided by k squared plus m squared minus chi tilde k k squared plus m squared chi tilde minus k. Now here we're in the exact same situation as we were with the harmonic oscillator, but I'll write it out again. So there's no dependence in the first term on chi, so when we do the path integral, this just comes out. So z0j, which remind you is defined as vacuum to vacuum in the presence of a source, is equal to e to the 1 I over 2 the integral d4k 2 pi to the fourth j tilde k j tilde minus k k squared plus m squared. I'm putting the minus I epsilon in because when we evaluate this we'll need it. And then we have the integral, the path integral d chi e to the minus I over 2 integral of d4k 2 pi to the fourth chi tilde k k squared plus m squared chi tilde minus k. Now, as with the harmonic oscillator, Z0 when the source is 0 is equal to 0, 0 in the presence of no source. The vacuum just goes to the vacuum, so this has to be equal to 1. And when we put j equals 0, this whole integral is 0, but it's e to the 0, which is 1. So we're just left with the last term, the integral, the path integral. So this whole path integral here is just 1, so we don't need it anymore. So z0 with the source is just equal to the exponential I over 2, the integral of d4x the integral of d4x 2 pi to the 4th j tilde k, j tilde minus k, k squared plus m squared minus I epsilon. Okay. So that's our major result for this part 1 video. And I will come back to part 2 to start getting the Feynman propagators and evaluating time-ordered products of fields. So thank you very much for watching. I'll be back in a few minutes for the next part.